Hi everybody! In this video, we're going to talk about how to do, I don't know how to pronounce this guy's name, so I'll just attempt it and say it's Dijkstra's algorithm for finding the shortest path between vertices. So go ahead and take 3 deep breaths and let's make this math easy. All right, so the goal of Dijkstra's algorithm is to be able to find the shortest path from all of the other vertices in a connected graph to one of the specific vertices. So this can be really useful for optimizing paths between vertices. So like let's say that we had all of the vertices represent different national parks in southern Utah. And then let's say that the edges between the vertices may be represented like shuttle routes that people could take between the different national parks. And then maybe the weights of those edges represent how much it costs to purchase a ticket for one of those shuttle routes. So this is an example I just made up, so I have no idea if there actually even are shuttles between national parks in Utah. But you could use this for any number of real life examples. And it may be useful to figure out the cheapest way to get to a specific vertex. So let's say that you were staying at a campground that was close to arches. And you wanted to know how much it would cost to be able to get to all of the other national parks from your campground by taking the shuttle routes. Well, you could use Dijkstra's algorithm to find the cheapest path from all of the other vertices, which are representing the other national parks, to Arches National Park. So the way that Dijkstra's algorithm works is you start by choosing the vertex that you want to find the shortest path to. So in this case, that is Arches. That's going to be what we call our end vertex, or like the end of the path. And we want to find the cheapest path from all of the other parks to Arches. So the way that Dijkstra's algorithm works is you start by choosing an end vertex. So I'm going to have the end vertex be Arches National Park because that's where my campground is. And I'm trying to find the cheapest route from all of the other national parks to that campground. So that's going to be my end vertex. And I'm going to mark it with a distance of 0 because the cost of getting from Arches to Arches is just 0 because you're already there. So that's going to be the distance. And then I'm going to mark it as my current vertex. So I'm going to designate my current vertex with a circle. And the way that Dijkstra's algorithm works is from your current vertex, you look at all of the vertices that are adjacent to it. So in this case, we have the vertex B and R and C because there are shuttle routes to Bryce and Capitol Reef and Canyonlands National Park from Arches in this hypothetical made-up situation I used here. So for each of those vertices that are adjacent to my current vertex, I'm going to calculate the distance to that current vertex. So the distance from Bryce to Arches, or the cost of that shuttle route, is $20. So the path from B to A costs $20. The path from R to A is $9. And the path from C to A is $2. And so once I've calculated the distance for all of the vertices that are adjacent to A, then I'm going to mark my current vertex as being visited, which means I'm just going to like cross it out. And then I'm basically going to repeat this process by choosing a new current vertex. And my new current vertex is going to be the vertex that is marked with a distance that is cheapest. So I have 3 different vertices here, and we have a 20, a 9, and a 2. So the cheapest one is the 2. So vertex C is now going to be my current vertex. And I'm going to look at all of the vertices that are adjacent to it that I haven't already visited. So if it's already visited, it's kind of like you're already done with it, so you don't need to look at it anymore. So the vertices that are adjacent to vertex C are R and G. And so I'm going to say, okay, well, if I went from Capitol Reef to Canyonlands and then to Arches, because remember, Arches is our end goal. So if I went from R to C and then followed this path to get back to A, how much would that cost? And in this case, it would be 7 to get from R to C to A, because it costs $2 to get from C to A, which we've marked here, and then it costs $5 to get from R to C. And so that will cost 7, and because that's cheaper, I'm going to replace the original path I wrote down with that number there because it's cheaper. If it's not cheaper, then I would just keep the distance that I already had written down. So if you find a new path that's cheaper to get back to A, you cross off the one that you found earlier. So that would be for R. And then for G, G doesn't have a path yet because it wasn't directly adjacent to A. So I would say, okay, well, if I went from G to C and then followed the path from C to A, that would cost $14 because it costs $12 to get from G to C, and then to get from C to A costs $2. So basically I do 12 plus 2, and that gives me the 14. And so that gives me the distance from G all the way back to our original endpoint, which is the goal because that's where our campground is. So once I've completed that for my current vertex, which is vertex C, and I've looked at all of the vertices that are adjacent to it, then I can mark it as visited, and I'm done with vertex C. Then I look for the next cheapest one. So essentially you kind of go through the same process over and over and over again. So I'm going to say, okay, well, out of the vertices I haven't visited yet that I have a distances recorded for, it looks like R is the cheapest one because I have 20, 7, and 14 as my distances, and 7 is the cheapest one. So now I'm going to look at R and I'm going to say, okay, well, this edge goes back to a visited vertex, so I don't need to worry about that. Same thing with this one, but this edge goes to one that I haven't visited yet. So I'm going to say, okay, well, the cost of getting from R to A, according to this, is 7. And so if I go G to R and then follow the path back to A, RCA, and get back to A, then that's going to cost me $15 because it costs $8 to get from G to R, and then the cost of getting from R to A, according to this path, is 7. And so I ask myself and I say, okay, well, is that cheaper than the distance that I already have recorded? So if I want to, I could even write this down. So the path would be going G to R to C to A, and that's going to cost 15 because 8 plus 7 is 15. But that number is not cheaper than the other route I've already found because this route that I found earlier is cheaper. So I'm actually not going to write that one down because it's not a cheaper route than the one I've already identified. So you only cross them off if it ends up being a cheaper route like it was here. Like it was cheaper to have 7 versus having the 9 that we found originally. So now I need to do the last vertex that R is adjacent to. So like if I look at this edge that goes to B, I can say, okay, well, if I go from B to R to C to A, the cost of that, so like if I go from B to R, that's going to cost 4. And then to get from R back to A is 7. And so that pathway is going to cost me $11. And because that is cheaper than the original $20 that I found on this other path, then I'm going to cross off the more expensive path. And then since I've looked at all of the vertices that are adjacent to R, which is my current vertex, then I'll go ahead and cross that current vertex off. Then I go through and repeat the process all over again. And I say, okay, well, out of my unvisited vertices, which one has the cheapest distance? So in this case, it would be B, because B has a distance of 11 versus G has one of 14. So I'd say, okay, that's my cheapest one. And I look at all of the edges that are leaving B. So this one goes back to a visited vertex, so I don't need to worry about it. This one also goes back to one that's already visited. And then on this one, if I look at this, it looks like G is not visited yet. So I say, okay, well, if I was to go from G to B and then follow the cheapest path for B, which is 11, so that would be going from B to R to C to A, because that's the cheapest path I've found for B. Then that would cost $12 because it costs $1 to get from G to B and then $11 to get all the way back to A. And because that 12 is cheaper than the 14 I found earlier, I'm going to cross that off and keep the 12. And then the next one I'll do is this one. So if I follow along this edge, it looks like to get from Z to B is costing 14, and then to get from B all the way back to A with the cheapest route is 11. So going from Z to B to R to C to A, that would cost, let's see, 14 plus 11 is $25. And so that would be the cost of going from Zions National Park through Bryce and then getting the cheapest route back to A. So once I've done that, then I can cross off B, and that means that that vertex is visited. Then I go through the process again and I say, okay, well, I have two vertices that have not been visited yet, and the cheapest one is G, because that one's 12 and the other one's 25. So I'm going to mark that as my current vertex. Most of the edges are going back to vertices we've already visited, so we don't have to worry about it. But this one goes to one that's not visited. And so I would say, okay, well, the cost of going from Z to G is 7. And then going from G all the way back to A with the cheapest route, which is G to B to R to C to A, that's 12. And so the overall cost of this is going to be 19. And because 19 is cheaper than 25, then I'm going to cross off my 25 path. And since I've looked at all of the vertices that are adjacent to G, and I've calculated the distances for them, that means that G is now finished and I can mark it off as visited. And I only have one vertex left, so that's going to be my current vertex, but all of the vertices it's adjacent to have already been visited, so I don't have to worry about it, and I can mark it off. And so once you've visited every single vertex in your graph, then the answers that you have here are the cheapest way to get from each one of those vertices back to your starting vertex. So for example, if I was asked, like, what's the cheapest path from Bryce National Park to Arches? Well, it's basically this one right here, where it say, well, the cheapest way to get from Bryce to Arches is to take the shuttle from Bryce to Capitol Reef, then take the shuttle from Capitol Reef to Canyonlands, then go from Canyonlands to Arches, and that's the cheapest route to get from Bryce to Arches. And Dijkstra's algorithm basically gives you all of the shortest paths back to your starting or end vertex. So these are the steps for Dijkstra's algorithm if you want to add them to your notes. They're also on your reference sheet if that's easier for you. But again, basically the process is you choose an end vertex, you mark that end vertex with a distance of 0 and start with it as the current vertex. And then from the current vertex, you look at all of the unvisited vertices that are adjacent to it and calculate their distances. And if the distance you find is cheaper than a previous distance you found, then you cross off the previous distance and record the new distance. And then once you've done that for all of the vertices that are attached to your current vertex, then you mark it as visited, cross it off, and then you look at all of the vertices that have a distance recorded, and the one with the smallest distance becomes your new current vertex. And then you go through and repeat that process over and over and over and over again until every single vertex in the graph has been visited. So why don't you guys try this example? This is an example that was in the textbook, and the vertices in this represent different cities in Washington State, and the edges between them represent highways between the cities. And so go ahead and try this on your own and find the shortest path to Yakima from all of the other cities that are shown in this graph. And then restart the video to see what the correct answer is. All right, so when I solved it, I got that the shortest path from North Bend to Yakima was 104, and you just take that direct route. So in my answers, I just used N for North Bend instead of NB. And the shortest route from Mount Rainier to Yakima was 96 miles. The shortest route from Packwood to Yakima is 76 miles. The shortest route from Eatonville to Yakima was 172. From Tacoma to Yakima was 160. And from Auburn to Yakima, it was 140. So that's the answer that I got. If you got the same thing, well done. If not, then feel free to ask me about it in class or try it again. And let's do one last example. Because remember, sometimes weighted graphs are not shown as an actual graph diagram, and sometimes they're shown as tables instead. So let's say that this table represented a graph that shows the shipping times between various shipping centers in different states. So let's say some company has like 6 different shipping centers in California, Texas, Kentucky, Georgia, Ohio, and Montana. And if we wanted to find the shipping time from all of the other states to Montana, then basically what we're trying to do is find the shortest path to Montana from all of the other states. So to solve this, I'm going to start off by choosing my N vertex. So my N vertex in this case is Montana because I'm trying to find the cheapest shipping time to Montana. So that's going to be my current vertex. And I'm going to look at it and see how many vertices are adjacent to Montana. So because I have a 7, a 13, and a 15 right here, that means to get from California to Montana, it costs 7 hours. And to get from Texas to Montana, it costs 13 hours. And to get from Kentucky to Montana, it costs 15 hours. So those are all of the vertices that are adjacent to Montana because they have like numbers in them, versus like these blank spaces show me that Georgia, Ohio, and Montana are not adjacent to Montana. So basically what I've done here is I have my current vertex, Montana. I chose all of the vertices that it's adjacent to, recorded their distances, and now that I have that done, I can mark Montana as visited, which means I don't really have to worry about these edges anymore. And because all of the edges are duplicated in a table, I can also cross off all of these because this 7 represents the same edge as this 7 over here. So I'm done with Montana, and now I need to choose my next current vertex. So the next current vertex is going to be the one with the smallest distance. So it looks like it's going to be California. And I say, okay, well, what vertices are adjacent to California that I haven't already visited? So California is adjacent to Montana, but I've already visited Montana and crossed it out. So the only other one that it's adjacent to is Texas. And so I would say, okay, well, if I go from Texas to California and then take the shortest path from California, which is just directly to Montana, how much is that going to cost? So because the cost from Texas to California is 5, and then the cost from California back to Montana is 7, the cost from Texas all the way back to Montana is going to be 12, because 5 plus 7 is 12. And since 12 is cheaper than just going directly to Montana from Texas, I'm going to cross this one out, and that means that my new distance for Texas is 12. And now that I've looked at all of the vertices that are adjacent to California, I can mark California as visited by crossing it out, which means I can cross off all of the edges that are related to it, both horizontally and vertically. Then I need to choose my next current vertex. So again, we're going through the same process for Dijkstra's algorithm. We're just applying it to a table instead of to a picture of a graph. So my cheapest distance is Texas right now. And so Texas is going to be my current vertex. And it looks like the only state that it's adjacent to is Georgia. And Georgia doesn't have a distance yet. So I'm going to say, okay, well, if I went from Georgia to Texas and then went all the way back to Montana by this cheapest path, I would get Georgia to Texas to California to Montana. And the cost of that is going to be 8 plus 12. Because the cost from getting from Georgia to Texas is 8, and then the cost of getting from Texas to Montana is 12. So if I add those together, that's going to be a cost of 20 for Georgia. And now that I've taken care of all of the things that are adjacent to Texas, I can mark it as visited, cross it off, and I'll go ahead and cross these columns off as well. I guess actually I should cross this column off. So Texas is now visited. Kentucky is my next cheapest vertex, so I'm going to make that my current vertex. And Kentucky is adjacent to Georgia and Ohio. So if I went from Georgia to Kentucky, that would cost 9. And then to get back to Montana from Kentucky would cost 15. So I say, okay, well, if I did Georgia to Kentucky to Montana, that would cost 15 plus 9, which is 24. But 24 is not cheaper than the path I already have designated. And so I'm not going to change that because it's actually cheaper to go from Georgia to Texas to California and Montana than to go from Georgia to Kentucky than Montana. So I'm not going to write that as a new distance because 24 is bigger than 20. So that part's good. And then Ohio doesn't have any distance right now. So I'll go ahead and record Ohio to Kentucky, which is 3. And then to get from Kentucky to Montana, that's 15. So the total cost would be 18 because 3 plus 15 is 18. And now that I've looked at all of the vertices that are adjacent to Kentucky, I can cross Kentucky out and mark that as being visited. And then I choose the next cheapest one. So it looks like Ohio is the cheapest. And Ohio is actually not adjacent to anything that hasn't already been crossed off. So I can just mark Ohio as visited. And then Georgia is also not adjacent to anything that hasn't already been visited. And so Georgia is done. And so basically what this tells me is that the cheapest route from California to Montana is just going directly from California to Montana, which is 12. The cheapest route from Texas to Montana is to go Texas to California to Montana, which will cost 12 hours. And Kentucky is going to cost 15 hours. Georgia is going to cost 20 hours. And this is the route that you would take that would cost 20 hours. And then Ohio is 18, and then obviously Montana is just 0 because you're already there. So that's the way that Dijkstra's algorithm works. And if you have any questions, I'm happy to help. So I hope you guys have a good day, and that's it for this video.